Welcome. Today we tackle 7.5, the fundamental theorem of calculus. This is the central fact around which all of calculus swings. And in fact, this will wrap up our discussion of real analysis for the semester, ending on a high note with the fundamental theorem of calculus. Although it's a little ironic that even though we are ending with the fundamental theorem of calculus, in fact, the fundamental theorem was one of the first things discovered in calculus. It was the great discovery of Newton that tied together the integration and differentiation that set the world on fire with the new ability to calculate things. So we end here and take a closer look at how integration and differentiation are related. So the derivative, recall, was motivated by the slope of a function. How quickly does the output change relative to a little change in input? But then it was actually defined in terms of functional limits of difference quotients. On the other hand, the integral was motivated by area under non-constant functions. And it was defined in terms of supremums and infimums of finite sums. So on the surface, it doesn't appear as though there really ought to be any great connection between these two ideas, the derivative and the integral. And so in fact, it's the fundamental theorem of calculus that reveals a remarkable inverse relationship between these two processes. So here it is, the fundamental theorem of calculus. There are two parts. Here's the first part. If a function little f goes from the interval a, b to the reals, and if that's integrable, and if big F also is a function from a, b to the reals, and it satisfies that the derivative of big F at x is little f of x for all x, then the integral of little f from a to b is big F of b minus big F of a. And the second part says, if little g is a function from the interval a, b to the reals, if that's integrable, and for any x in the interval I define big G of x equals the integral from a to x of little g. Maybe for this part I imagine there's my function g, I have a little a, little b, and it's x somewhere in there. The big G of x represents that area. Well, then it turns out a couple things. Then big G is continuous. Okay, so that's interesting on its own. Big G is continuous. And in fact, if little g is continuous at some c, I'll put a c in there, then in fact my function big G is differentiable at c, and the derivative of big G at c is little g of c. Okay, so there's a lot of stuff wrapped up in these two statements. It's worth pausing for a minute if you need to draw some pictures and kind of get a sense of these things. Think about hypotheses, and we'll just take some time proving the two of these things. Just a quick note, the first part is often thought of as kind of the computational part of the fundamental theorem, and the second part is more theoretical. The second part sort of shows more cleanly, I think, the relationship between integration and differentiation, and the first part is great if you actually want to compute your definite integral. You find an antiderivative and evaluate at the two endpoints. Now, historically, point number one actually came first. Although it's kind of curious, textbooks today, modern textbooks, will often switch the order. What we call 2, they will call the fundamental theorem of calculus part 1. They focus on continuous functions, and modern textbooks, like calculus textbooks, will often use the second part in order to prove the first part. But we will prove the two of these things independently. All right, let's begin. Fundamental theorem of calculus part 1. Here's the statement of the theorem again. And the proof. So let P be a partition of the interval from a to b. So I've got my x0 through xn. And we're going to consider this big F. And on each subinterval, let's apply the mean value theorem. So I have this subinterval x sub k minus 1 to xk. And I can find some little c inside that subinterval such that this equation is true. Now, I'm applying the mean value theorem, and I need to apply it on my function f. So what are the hypotheses for the mean value theorem? My big F has to be continuous on the closed interval, so like ab, or this x sub k minus 1 to xk, and it has to be differentiable on the interior of that. And big F is differentiable on all x in the closed interval. Now, if it's differentiable, then certainly it's continuous. So in fact, both of those are satisfied. So what I can do, I can multiply both sides by that denominator, and I get my expression that the difference of big F at the two endpoints is this expression right here. And then lastly, I can say, oh, that derivative, that's really just little f. That's little f of that midpoint, that interior point. Okay, so I'll take this equation and put it at the top of the next slide. There we go. And where do we go from here? Let's consider the lower sums of little f over the partition and the upper sums of little f over the partition. So by definition, the lower sum is the summation of all these infs. So it's the infimum of the function values times the width of the interval. And by definition, my upper sum is the sups, the supremums of the function values over the interval times the interval width. But look what I have here now. I picked something sort of in between my min and my max. So this f of c sub k, well, c sub k is a point inside that interval. So certainly f of c sub k is at least as big as the infimum of all function values. And f of c sub k, well, it can't be any bigger than the supremum of all function values. So I have that little f of c sub k times the interval width is going to lie between my lower sum and my upper sum. But then, exactly what I have at the very top of the screen, I can replace my little f of c times that difference with the difference of big F evaluated at the two endpoints. And now here's where the real magic happens. Do you see how that will simplify? That is a telescoping sum. So in fact, all I end up with is big F of b minus big F of a. This inequality is independent of the partition. So for any p that I pick, this inequality will hold. So in fact, I could take the sup of all the lower sums, and that is the lower integral, and the inf of all the upper sums, that's my upper integral, and I still have the inequality. But what do I know about my function little f? Little f is integrable. Those two integrals, the lower integral and the upper integral, those are equal. And so I finally arrive at the equation that the integral of little f from a to b is in fact big F of b minus big F of a. And we're done, and that's the fundamental theorem of calculus part 1. Let's move on to FTC part 2. Okay, so in this case we're given this function big g of x, that is the integral of a to x of g. And the real thing that we want to show is that when I take the derivative of big G, I end up with little g, at least at the points where my function little g is continuous. The first thing I'm going to prove, though, is just the fact that big G is continuous. So let's focus on this statement for a while. Why should that be true? The first thing that I want to note is that at least my little g has to be bounded. Now, why should that be the case? Here, it's conceivable, there's a, b, that maybe my function little g has an asymptote, but maybe it's actually defined somewhere. So it looks like this. It becomes arbitrarily high, but at that moment where it becomes arbitrarily high, has some function value lower down. Is that possible? If g is integrable, can g be unbounded that way? If it's not bounded, if g really goes on up forever and ever, then any partition is going to have some kind of interval where g attains arbitrarily large positive or negative function values. I make a partition, and one interval of that partition is going to contain arbitrarily large function values. And so that tells us that the big M sub k, or the little m sub k, would not exist. And so that whole summation that gives me my lower sum and upper sum ceases to exist and would not be integrable. So there really is some big M greater than 0, so that the absolute value of g is bounded by the big M for all x. Okay. Let's take some x greater than y in this interval a, b. So I've got a, b, there's a y, there's an x. And what happens if I take the absolute value, the difference big G of x minus big G of y? Well, remember what big G represents, that's just the integral. So big G of x is the integral from a to x of little g. So big G is that area. Big G of y is the integral from a to y. So that area. And what's going to happen when I subtract them? Well, I'll just end up with the integral from y to x of little g. And then I can pull the absolute value on the inside. There's our generalized triangle inequality. But now I can use the fact that my little g is bounded. So here's where that previous discussion comes in. There's a big m in there somewhere where the function doesn't exceed that m. So in fact, the integral from y to x of g is going to be less than or equal to that height, that big M, times the interval width. So how does this help us? Does this tell us anything about the continuity of big G? Well, yes. In fact, this shows us that big G is uniformly continuous on the interval from a to b. Now, uniformly continuous is actually stronger than what I really needed. All I really wanted to show was continuous. But if I took the expressions on the two ends and I divide by x minus y, I'd end up with g of x minus g of y over x minus y less than or equal to m. And this is basically showing me that the slopes are bounded. The slope of big G never exceeds capital M, which is what I need for uniformly continuous. Here is the definition of uniformly continuous again, and a little proof of that fact. I'll not spend any time on it, but if you'd like to pause the video at this point and take a closer look, feel free to do that. All right, let me move on. The next thing I want to prove is that if my little g happens to be continuous at some point c, then big G is differentiable at that c, and that big G prime of c equals little g of c. So my picture, my function little g is continuous at c, and I want to show that the derivative of big G at c is actually g of c. So let's assume that little g is continuous at c. What this means by definition is that given any epsilon greater than 0, there is some delta greater than 0, such that, now I'm going to use t's, so I'll call this the t-axis. If t minus c is less than delta, so there's some delta, so if t is within delta of c, then g of t minus g of c is less than epsilon. So this delta epsilon relationship exists around the point c, showing us that g is continuous at c. Now notice something interesting here. This g minus g of c is a function. Now g of c is a constant, but I can imagine a constant function. So g minus g of c is a function, like how I might say that g minus f is a function when I just take the difference of two functions. And what I have in the absolute values, that's that function evaluated at t. So let's imagine that if x minus c is less than delta, so I have some x here, and let's imagine that the x minus c, that difference is less than delta. Then over this interval from c to x, well, it certainly has to be the case that the function g minus g of c is bounded. Because if c minus x is less than delta, then certainly all of those t values that are in there, the t minus c will be less than delta. And I have my original situation. So t minus c being less than delta will tell me that the function is bounded by epsilon. So here's the statement that's going to be most important for us. When x is within delta of c, that implies that the integral from c to x of the absolute value of this function is less than epsilon times x minus c. In fact, we saw something like this earlier, right? When I knew that my function g was bounded, and so I had g from y to x was less than m times x minus y. So it's the same kind of idea here. I've shown that this function in absolute value is bounded by epsilon, and so the integral is less than epsilon times x minus c. All right, so it seems like a strange thing to think is important enough to put a star by, but this is a result from little g being continuous. Okay, now we're going to take an aside, so keep that in your mind. We'll do some other work and then bring this star fact in just a couple minutes. Okay, so remember where we're going with this. Ultimately, we want to show that big G prime at C is little g of c. Well, the derivative g prime of c can be written this way. Well, if the limit exists. It's the limit as x goes to c, big G of x minus big G of c, all divided by x minus c. I want to show that this limit exists and that it actually equals little g of c. Well, I can modify this a little bit. Let's replace the big G of x and the big G of c with what they represent in terms of integrals. And then I can combine these two integrals together, and that gives us the integral from c to x of g. And now here's really the question. The limit of this guy, this is just a limit of values. Does that thing equal little g of c? How do I determine if little g of c is this limit? Well, I need to put those expressions as a difference in absolute values and show that I can make the absolute value arbitrarily small. Let's simplify this absolute value. The first step is kind of a clever substitution. This g of c is the same thing as this integral expression over there. G of c is just a constant. I take my constant and integrate from c to x, and then divide by x minus c, and I just end up with that constant value again. But now, these two terms inside the absolute value can be combined, and I get the absolute value of this expression. One last step. Now let's take the absolute value and bring it inside, and I get less than or equal to 1 over x minus c, integral from c to x, absolute value of g minus g of c. And this looks like something we saw in the star expression. So let epsilon greater than 0 be given by star. There is some delta greater than 0, such that when absolute x minus c is less than delta, that implies that the integral from c to x of absolute g minus g of c, that function, this whole integral is less than epsilon times x minus c. So look at the benefit that gives us. If the absolute value of x minus c is less than delta, then when I take my difference, when I take that big absolute value, well, I know from before it will be less than my next expression. But then by using the star, that integral itself will be less than epsilon times x minus c, and that product gives us epsilon. All right, and so after all of that, that is actually showing us that indeed big G prime at c equals little g of c. I've shown that this difference in the absolute values can be made arbitrarily small. Okay, so I know that we've really waded through the weeds a lot in this problem. We got down into a lot of detail. But there it is, and each of the parts individually isn't so bad, and it was kind of interesting. We used a lot of stuff from over the whole semester. Things about convergence of limits, the mean value theorem, and all kinds of properties of the integral. Alright, and that just takes us to the homework. Section 7.5, problems 2, 4, and 8. I restated the fundamental theorem of calculus here again, just to bring us back up to the surface and make us realize what it is that we do all this for. And also to let you know that as you do those homework problems, you'll be using the fundamental theorem of calculus. Be a little bit careful. The problem is really understanding the theorem deeply. So be careful in particular with hypotheses. When you have a problem that involves a function g and you want to use the fundamental theorem of calculus, be sure that g really satisfies the hypotheses that you need. Alright, so that is it. Get to those homework problems, and as always, give me your questions if you have them.